Hi everyone, I am Srinivas Basha, postdoctoral fellow, Department of Biological Sciences, University of Arkansas, United States of America. In my today's presentation, I will be discussing about my research work, which is a stability comparison between natural archaeal and engineered archaeal bacterial heat-shock protein subunits and their oligomeric complexes. Coming to the introduction part of my research work, Hyperthermophilic archaea family Sulfolobaceae express group 2 chaperonins, which are also commonly referred to as heat shock proteins due to their upregulation upon heat shock. There are three subtypes: HSP alpha, HSP beta and HSP gamma. HSP alpha and HSP beta subunits are most thoroughly characterized and are reported to assemble into a nanomeric double ring structure. These HSP complexes are known to play a significant role not only in the folding of nascent proteins but also in the production of cytosolic proteins under the conditions of environmental stress. In this context, there has a significant interest in re-engineering the system as an enzyme production platform for use in industrial applications. The first such a prototype platform was called rosettasomes, an 18-mer homomeric complex composed of subunits which are fusion protein of archaeal HSP beta, the cohesion type 1 from Clostridium thermophilium. Enzymes endowed with the dockerin type 1 binds to the cohesion and the sequester enzymes to the HSP complexes. We previously demonstrated that use of cellulose charged rosettasomes and acidic or alkaline pre-treated wheat star corn ferric crops results in an increasing lignocellulose deconstruction and polysaccharide reduction to fermentable sugars, for example glucose. However, the twofold enhancement observed was not sufficient to render the system economic viability for industrial applications. More recently, we re-engineered the HSP system into a next generation mobile enzyme sequestration platform with the goal of increasing the stability of enzyme platform complex. The purpose of the study was to determine the relative stability of different HSP subunits and fusion construction, for example HSP beta co, to determine if homomeric or heteromeric complexes exhibit greater stability under high temperature or low pH reaction conditions. Second one, optimize MSP and enzyme components to achieve 6-fold or 8-fold increases in enzymatic efficiency over equimolar concentrations of the same enzymes free in solution under high temperature or low pH reaction conditions. I applied the following research techniques: gel electrophoresis and transmission electron microscopy resolve HSP complexes. Circular dichroism shows each subtypes form a similar 3D structure. Differential scanning calorimetry reveals differences in the thermodynamic stability of individual subunits as well as differences between distinct homomeric or heteromeric 8-mer complexes. Coming to the results of my study, in this slide figure 1a indicates the period of proteins by SDS page. HSP alpha and HSP beta migrates to 60 kD. HSP beta co migrates higher to 75 kD, while the figure 1b shows CD analysis of natural and engineered protein. In this figure, we observed negative velocity bands at 222 nanometers and 208 nanometers, which confirmed our protein has a good secondary helical structure. In this slide figure 2, we analyzed thermostability by DSC. We observed natural protein had a more thermostability than engineered protein. The HSP alpha and HSP beta are most thermostable with melting temperature at 95 degrees, while HSP beta co was slightly lower, melting temperature 88.3 degrees due to the presence of a fused cohesion domain. In this comparison, similar Kagawa et al. 2003 had also reported similar results where the thermostability was found in the range of 95 for alpha and beta. In the slide figure 3, it indicates that HSP complexation is verified by TM1 native gels, HSP alpha and HSP beta co-homers and HSP alpha beta heteromers formed a double ring structure. Native page indicates that the presence of ATP and MgCl2, alpha beta formed a distinct homomeric complex bands with 1:1 mixture of alpha beta co-formed a distinct heteroalgomeric complex bands visible in native gel. In this slide, figure 4 shows thermal stability of protein complex were analyzed by DSC. HSP alpha and HSP beta co-homomeric complex and HSP alpha beta co-heteromeric complex indicates that homomeric complex more thermostable than heteromeric complex. Even though Kagawa et al. Reported high thermal stability for combination of alpha beta complex, but in our study we got slightly lower stability that could be due to the presence of fused cohesion domain. In our study we observed HSP alpha high thermal stability, so we focused HSP alpha for the studies. In this slide figure 5, stability of HSP alpha different pH conditions, we clearly observed that no changes at pH 2 to 10 conditions. In this slide figure 6a, it shows the structural comparison of HSP alpha and BSA reveals that each are globular, largely alpha helical with similar quantities of trypsin cleavage sites 72 and 78 respectively. Both have similar sizes 60 and 66 kd, number of amino acids 560 and 607 respectively. HSP alpha is less resistant to trypsin at variable concentrations. HSP alpha is 30% more digested than BSA. Preliminary results for specific aim one also provided. Specifically, our data shows that HSP alpha has highest thermal stability compared to HSP beta and beta co. HSP homomeric complex are more thermal stability than heteromers. HSP alpha retains its helical secondary structure when subjected to various pH conditions. HSP alpha has high thermal stability, more stable and flexible backbone structure than HSP beta and beta co. In this slide figure 6a shows structural comparison of HSP alpha and BSA. In this slide figure 7, express the multiple sequence element of natural and engineered proteins. It has shown hydrophobic residues or yellow colored amino acids. Due to the presence of hydrophobic nature, these proteins observed good thermal stability. In this slide figure 8 illustrates that HSP alpha subunits 3D model and a homomer top view and side view structure. The outlined structure of the views shows itimer. Coming to the conclusion part of my study, I conclude that HSP alpha and HSP beta and engineered beta co were all purified to homogeneity. The CD spectrum of each subunit reveals a largely helical structure. Comparison of DSC thermograms, each subunit reveals that HSP alpha and HSP beta are most thermostable with the melting temperature at 95 degrees, while HSP beta was slightly lower. HSP complexation is verified by TM1 native gels revealed 8-member complexes. HSP complexes were analyzed by DSC. Homomeric complex more stable than heteromers. So HSP alpha further taken experiments to know the pH and structural conditions. We found that HSP alpha retains its helical secondary structure when subjected to pH conditions from 2 to 10. So HSP alpha was subjected to trypsin digestion compared to BSA. HSP alpha is cleaved by trypsin to large extent than BSA, indicating that HSP alpha has a more flexible backbone structure. Finally, I would thank to my co-supervisors and authors for contribution and helping in this work. I also extend my thanks to my research supervisor, Dr. Michael Sebals, for giving this opportunity. I also thanks to Professor Suresh Kumar for this collaboration with my lab, and thanks to everyone who participated and also who watched this video. I would like to thank University of Arkansas and National Science Foundation for funding this project. Thank you so much.